Good afternoon, ladies and gentlemen. It is a pleasure for me to participate at the International Conference on Smart and Innovative Agriculture, ICOSIA 2020. My name is Rudiati Evi Masito from Department of Agricultural and Biosystem Engineering, Faculty of Agricultural Technology, Universitas Gadjah Mada. Today, I'm going to present the paper of development of calibration model for pH content of intact tomatoes using a low-cost fish and IR spectroscopy. First of all is introduction. One of quality parameters of fruit is pH, which represents acidity level and is used as indicators of taste. During ripening, tomato experience physiological changes, which involve starch to sugars conversion, flavor formation, and pH increase. In general, pH or acidity was determined using titration method, pH meter or acid meter, which not only destructive but require sample conversion to liquid, thus involve intense work and long time analysis. Titration methods also lead to subjective measurement and highly depends on the skills of the analyst. Therefore, it is unpractical for large quantity and routine analysis. On the other hand, spectroscopy and chemometrics have developed which offer rapid and non-destructive analysis. At present, methods for determining pH or acidity of fruit were carried out by infrared spectroscopy. Infrared spectrometers with a wide infrared range above 1000 nanometers are used to determine acidity in many kinds of fruit. They provide rapid and accurate prediction, however, require high cost for the purchase of the instrument. Other type of spectrometers working in the visible and short-wave near-infrared or FIS and IR at 350 to 1000 nanometers is also available and can be used to determine quality parameters in fruits. It has several advantages. Weak absorption of FIS and IR energy for water molecules make the wave range suitable for detecting small concentration of objects, since it will not be distracted by water spectrum, which is the largest components in fruit. The previous FIS and IR spectrometer were benchtop model or handheld instrument for field application. They provide easy and accurate measurement, but the costs are still relatively expensive. Therefore, the use of low-cost spectrometer will be beneficial for farmers or industries with a low budget. This research aimed at developing calibration model for determine pH of tomato by using a low-cost FIS and IR spectroscopy and chemometrics analysis. The total of 99 tomatoes were purchased from local markets in different colors, green, orange, and red, which represent level of maturity to obtain sufficient variability of the samples. The fruits were stored at 25 degrees Celsius prior to spectra measurements. Of 99 samples, 50 samples were used for calibration and 49 samples were used for prediction. The spectroscopy equipment consisted of a flame T-FIS and IR spectrometer with tungsten halogen lamp, reflection probe, and a sample holder. The wavelength range of the spectrometer was 350 to 1000 nanometers. The fiber optic probe was clamped by a retort stand and the sample was placed 1 cm above it on a self-developed sample holder. A white reference was used to obtain the relative reflectance before spectra acquisition. Spectra were collected in reflectance mode using OceanView software. After spectra measurement, each sample was blended into juice including the peels. Acidity level in terms of pH was determined from the liquid of the tomato juice using a digital pH meter. Measurement of pH was done in triplicate and average. The reflectance of spectra of tomatoes were transferred into Excel file, which were then imported to the unscrambler software for spectra preprocessing and analysis. Several pre-processing methods were applied, including normalization, baseline correction, Savitsky-Golay derivative, multiplicative scatter correction, and standard normal variate correction. Original and pre-processing spectra were used for multivariate analysis, including principal component analysis and partial least square regression. PCA was used for data exploration to find deeper insight of the large data obtained from spectroscopy instrument, while PLSR models developed using full cross-validation method were used to quantify chemical content or pH. The performance of calibration model were assessed in terms of coefficient determination of calibration, standard error or of calibration and prediction, bias, and ratio of performance to deviation or RPD. Now we are at result and discussion session. Of 99 tomato samples contain pH in average of 4.5, minimum of 4.2, maximum of 4.9, and standard of deviation of 0.2. The narrow range of pH may affect the calibration model. The figures show the MSC spectra of all tomatoes, which were classified into 3 classes based on color: green, orange, and red. Only spectra between 500 to 900 nanometer were presented, since spectra below 500 and above 900 nanometer were very noisy. In general, there were increase in reflectance value from 500 nanometers, then followed by decrease to around 675 nanometer. Relatively low and stable absorbance were noticeable at 720 to 900 nanometers. Those are weak absorption of water molecules, which were captured as low values by the VIS and IR system. The system had a low spectra resolution of 0.22 nanometer, therefore could not detect small absorptions. At 675 nanometer, green tomatoes had the lowest reflectance value, which means they had the highest absorbance value, followed by orange and red tomato. Those absorbance values were due to the absorption of chlorophyll. Green tomatoes, which have the highest chlorophyll, will have high absorbance compared to orange and red tomatoes, which have lower chlorophyll. The lowest reflectance value between 500 and 580 nanometers were found at red tomatoes, followed by orange and green tomatoes, which mean red tomatoes had the highest absorbance at 500 to 580 nanometers, while green tomatoes had the least. The absorbance of 500 to 580 nanometer was due to lycopene pigment owned by red and orange tomato. Principal component analysis was used to visualize large variables such as spectroscopy data. PC1 and PC2 scores explain 99% of total variance, but by using PC2 and PC3, tomatoes can be clearly classified into green, orange, and red groups, as shown in the left figure. The PC2 separated tomatoes into green, orange, and red, and green and orange tomatoes had negative value, while red tomatoes had positive value of PC2. From the right side of the figure, we can see that the peaks at 675 nanometer showed positive loadings of PC2 for red tomatoes and negative loadings of PC3 for orange and green tomatoes. Positive loading at 675 nanometer indicated high reflectance but low absorbance, while negative loading indicated low reflectance but high absorbance. The absorbance value at 675 nanometer were absorption of chlorophyll. Therefore, tomatoes reflected red colors. This phenomenon was reflected in the left figure, by which Using PC2, tomatoes were grouped in green and orange located in the left side of PC2 and red located in the right side of PC2. Of several preprocessing methods used in this research, the original spectra yielded the best result for pH determination at wavelength range of 527 to 799 nanometers. The coefficient determination of calibration of 0.9, the SEP of 0.11, and bias of 0.007 suggested that the model was applicable for screening and approximate calibration. However, RPD of 1.17 was lower compared to those reported for tomatoes and grapes from other research. The low prediction result might be due to narrow range of pH used in this study. The figures show the regression coefficient of PLSR using original spectra, in which the spectra were very noisy, but several peaks could be noticed at 560, 670, 730, and 760 nanometers, which might have important roles for the calibration model. Waveband at 560 was assigned to lycopene, while waveband at 670 and 760 were assigned to chlorophyll A and water. However, it is difficult to identify which absorption bands specifically contributed to pH prediction. Finally, we can conclude that calibration model resulted in coefficient of determination and standard error of calibration of 0.9 and 0.04, while prediction model resulted in SEP, bias, and RPD of 0.11, 0.007, and 1.17 respectively. The fish and air spectrometer has proven to be a promising tool for measurement of pH of intact tomatoes. Thank you very much for your attention.